Hi, this is lecture 10 for Math for Designer, and today in this lecture we are gonna learn about two-dimensional transformation with vector. Yeah, so these are the dimensional, and we're gonna achieve that two-dimensional transformation with vector. So it's both vector. If we will touch just a little bit, and then we will see how we can use that to describe or to compute transformation in two dimension or on a plane or a piece of paper. There was this pre-excited no longer exists. This web page no longer works, so apologies for that. But just an idea that there was this web page where you can upload an image on the right and input some numbers in these four boxes on the left. And once you hit submit, then this image will be transformed or will be changed to the same image, but with different scales or different proportions, or then they have all those sort of things. Could go on, depending on the phone numbers that you put in. So it works kind of like if you have like some knobs that you can move, you can turn to change the image to the new image that you want. Well, maybe we don't have that, but of course we are going to learn about this week and next week. Actually, this topic has a word matrix. If you notice, it's small, but it's there. Matrix, and we're gonna learn about matrix next week. But before we can get to the matrix, we have to step back a little bit and see what we can do when we use transformations using only vectors. And yeah, that's the first section. Before we go into two-dimensional, we can again step back to just one dimension, which is maybe this requires some math knowledge, but we all live in the three-dimensional earth or three-dimensional world. Three means it's the degree of freedom. It is the direction we can move without conflicting with each other. So you can walk up, you can walk forward or backward. You can move to the left or to the right, and you can go up and down. If you have a plane or have a way to move in that direction against the gravity. But that's what it means for three dimension. There are three. You can define any kind of movements using only only allow three directions, and then every other movement will be a combination of these three movements. So that's the world we live in. Well, when we go back to two dimension, this might be more familiar because we studied about this already, which is about graph. A graph has two axes. The x-axis, which can be thought of as the horizontal direction, and also the y-axis is the vertical direction. And once we have these two directions, then we can express any point on the plane or on this piece of paper, like in terms of the two numbers. How far away in the x direction and how far away in the y direction. And that's going to be a point. And that's going to be an instruction of how you can get to that point from the center. So that's two dimension, which we're gonna visit in a bit, but we have to go back a step, right, and think about one dimension. Like one dimension means there's only one direction we can move to. So let's say if you move in this direction, then that's all you can do. Right, but you can still move further away from that point. Yeah, this is just a unit of movement. You can also move backward. So that's one dimension. Think of it as an ant walking on a rope, walking backward, walking forward. There's no escape from that unless you jump out of the rope or something. But let's find that's one dimension. And actually that one dimension can and also should be thought of as the real number line. Real number line. So it's a line. that has all the real numbers. The way we can achieve that is if we make some arbitrary point to be 0 and have 1 somewhere to the right of that number, and then we put that as a unit, and then we continue on the right. We put 2, 3, 4, 5, so that the gap are the same. Can go on forever to the right, and that's what the arrow here means. And also we can go back to the left using negative numbers. So if you go back 1 step to the left, you get to the number -1. If you go back another step to the left, you get to the number -2, and so on and so forth. So 1 dimension, like a point on a line, it can also be thought of as a number on the real number line. And the nice thing about number is once you have numbers and you can compute, you can calculate a lot of stuff about that. And so that's where we are going to start. We have 1-dimensional transformation on the real line, the real number line, abbreviated as the real line. What does it mean to transform on a line? So yeah, let's start simple. If you have something on a line, let's say you have a segment, or in this case, it was an interval. If you remember, like long time ago when we talk about sets, or when we talk about inequalities, we talk about intervals. So I think of this blue orange stick as an interval from 1 to 2, and to be correct, it should be on the line, like over the line on top. But I move it up a little bit so we can see it a little bit easier. But that's a line. That's a stick on the line that occupies the spaces between 1 and 2. And now we are gonna see what can we do with it. What kind of actions can you take if you have this piece of stick on a line? And there's not much to do because again there's only 1 dimension. And so you can go forward, you can go backward. Maybe you can expand or multiply or scale up. But still, everything is limited to just 1 direction. And so on that line, because of a limited option, then there are only 2 simple transformations. So you can move a line. Just move it, push it backward or forward. And the formal definition is translation. Just you translate language, maybe from Thai to English. There's a way of translation from one to another. But in math, translation simply means you move an object from one point to another. So you can move that line, or maybe I should say move the line segment. That should be more accurate. Oh yeah, I said it above but not here, down here. And another option is to scale the line. And scaling, just like you scale an image in an application or on your laptop, when you scale it up or down. And scale up means you get a larger image. Scale down, you get a smaller image. You can also scale by a negative number. We go over it a little bit. Maybe even if you say that scaling, like it just there's only 1 action you can take, and there are actually like 4 different results after the scaling. And also there's some formal definition, which is the dilation. And personally I don't like it, but yeah, that's something to think about. That's more general than scaling. So yeah, if I give you, or if you give me a line segment, then there are only 2 possible actions you can take. And another formal definition is we can denote a transformation by a function t of x. And again, this may be kind of abstract, but it's gonna be a lot easier if you write it this way. So remember the function f of x. Like f of x, f is nothing but a name of a function. And if you don't know what to name the function, then just name it an f as a default, f for the function. And x is a variable. You can put you can put something you want into this function and do something about that. Maybe use some computation, translate that, or interpret that in some way, and then put output as a result. Here we are gonna have a function where x is the starting point. Oh, sorry, I should say that is a point. Yeah, just say it's a point or a number, because again, once we make the real line as a model, then everything on the line can represent a number. So that's a function. You put a number in, you get a number out, and that number and the result is a point where it gets transformed to. So you change from one number to another by some function. And yeah, there are two let's say two basic transformations. There could be like more sophisticated or more fancy ones, but for now, there are only two. The first one is simple one, a translation. If you move one point to a new point, then you simply get a function that you just add that number to by another number. So for instance, if you have a line here, or an interval, a line segment, or an interval from 0 to 1, and you transform and you move every point here by adding everything by 3, and that's the same as moving. That's the same as translating by 3. It's kind of a fancy word. Or you can just use your understanding and describe this transformation as moving points to the right by 3 units. Is just a number 3, but just to be general, just move everything by 3 units. And you can see that the point 0 gets moved to point 3, the point 1 gets moved to point 4, and also everything in between also gets moved by the same amount. So that's a translation. Nothing fancy yet, but also just a note there that since this a can be any number, then you can also have a negative number. This might be the place where it gets slightly confusing, because the formula is x plus a, but we have x minus 2, and so somehow you have to change that to you have x and then you translate by minus 2. What does it mean by translating by a negative number? Now, if you translate something by a positive number and move to the right, then translating by a negative number would move everything to the left instead. And so if you start from the same interval or the same line, like 0 to 1, and let's say you have a different one, let's say t2, let's give it a different name. You move everything by 2 steps to the left. Then just move them to the left. So this point 0, it gets moved to minus 2, because 0 minus 2 is minus 2. This point 1 gets moved to minus 1. Because again, p of 1 is 1 minus 2, which is minus 1. And also everything else in between also gets mapped to a new point to the left. So this is a translation by a negative number. So you just move to the opposite direction from the positive one. Okay, nothing fancy yet for the translation. But if you see the images like before and after, there's one interesting note that you can make, or maybe two if you are very observant. The first thing the first observation you can make is that the size or the length of this line is preserved. Meaning that after the transformation, if you start from a line segment of length 1, then at the end you're gonna still get a line segment. Get a line segment of length 1. length is unchanged. And no matter you move to the left or to the right. And that's one simple fact. Another one is it's actually related to inequality. I noticed that if you have 2 points, let's say if in the original one 0, the green point is to the left, and 1, and the red point is to the right, then no matter what how many steps or no matter how you translate that, then the end result still have the green point to the left and the red point to the right. So in this case, another thing that is preserved is the order. The ordering of the points is also preserved. Which at this point it might be obvious, or it may be clear, it can be trivial, but if I ask you to prove that, then of course it's a little bit difficult to prove. But actually we can prove that because we learned something about inequality, didn't we? Right, when we talk about the order on the line, then we say that some point or some number is smaller than the other number, is smaller than another number. Or in this case, it also say that this point is on the left, is to the left of y. And the translation, if you have all the points, and if you translate everything by the same amount, then we should still get the same inequality. Because in the inequality, within the subject of inequality, we have a property that we can translate. We can add the same number on both sides and preserve and keep the inequality symbol. So again, it seems like an easy fact, but you actually have to rely on inequality to prove it. But we can. So that's one thing, translation. The first thing you can do on the line, if you are an ant, you get moved. And the other one is dilation. And it says dilation, but there are actually, let's say, four different ways to can dilate. The formula is simply t k times x. If you give me value x, I multiply them by k and give you back the value. So for instance, if you consider the transformation tx equals to 3 times x, and so the point 0, if x is 0, then the transformation, you get 3 times 0, which is of course 0. That point hasn't changed. But if you have 1, if x is 1, then after the dilation, after you multiply that, you get to 3, which is further away from 0. And also all the points here gets dilated or gets scaled to various points between the lines. So this if you multiply or if you dilate by a constant, then you get this kind of new line. In this case, it's a factor of 3. But on the other hand, if the number is negative, then similar to earlier before, if you consider each point separately, if you start at 0 and look at this formula, if x is 0, then after the transformation, after we compute that, we get a new point which is 0. But if you start at 1 is a positive number. If you plug 1 into the function, then you get minus 1 over 2. Minus 1 over 2 is, of course, minus 1/2. So this point 1, and once you plug into the function, once you transform that, you get to a new point, minus 1/2. That's what we have. And of course, everything else is is between these 2 points. And again, here, just on a few notes here. First, you can see that if you dilate or if you multiply by a positive number, then the result still have the same ordering. So if the first point is on the left, then the final point after translation should still be on the left. and if it's positive. But if it's negative, in this case it is negative 1/2. Right, then the ordering swap or reverse. So 0 starts on the left, 1 starts on the right. But after the transformation, right, at the end point of 1 becomes minus 1/2, which is on the left, and 0, which is 0, becomes the point on the right. As you can see, maybe it's slightly difficult, like from the shade of this image. So that's a lesson for you. Oh, and also, yeah, another note is about, since we call that a scaling, you can see that the size is multiplied by k, and actually it should be absolute value of k to be precise. If you multiply or if you dilate by a factor of 3, then the new line should be 3 times as wide as the original line. And of course you can see it from here because the original line has length 1 and then the result has length 3. It's 3 times larger, so 3 times wider. And likewise, here below here we have a negative number. We flip the line, but nevertheless the scale, like we start from a line of length 1 and the end result is a line of length 1/2. The size is shrink in a half. Now you can say that the size is half times the original one. It's wider by a half, so it's shrink by in half. So yeah, that's a relation. If you just perform a single operation, and then you can see this to a kind of boring, I guess. Oh, by the way, yeah, I should also mention that in the relationship with inequality, if you have x less than y, then a times x is less than a times y. And if a is positive, as we saw from several weeks ago, if a is positive, then the result keeps the same ordering. Again, which makes sense. And on the other hand, if the multiplier, or in this case it's a scale, is negative, then the order is flipped. This new point. If x is on the left, then a times x is on the right. Because something is flipped. And so there's a dilation. Also some inequality to prove the new result. And we have two operations. And of course this seems boring, right? Because yeah, there's nothing much there. But if you notice, you may ask, oh, you can add, you can multiply, but can you do them both at once? Can you have 2x plus 1? Or minus x plus 10? Or x over 2 minus 7? And of course, the answer is yes, you can do that. And these are also transformations. But the reason we didn't mention that at first, because we can mention it here. So once we break down into the basic transformations, then we can think of a more advanced transformations as a series or a sequence of transformations. In this topic, we call it composition. And again, fancy word, but at least the word compose has a English meaning, which means to collect things and put them together into a single piece, a single bigger piece. And here, if you are given two transformation T1 and T2, then we can compose it. We can combine it into a single new transformation. And the notation is the small circle, which you can call it as an OR. In this case, you could read it as T1 or T2. Or, compose or whatever you want to. This is how we write it as the new composition. But the way you compute it is the function on the right. We didn't learn about function composition or composite function, but it's actually one of the basic operations you can do. But here, yeah, we have this one. T1 open parenthesis, T2 close parenthesis. This is here like we treat T2 of x. We treat this blue part as a single number. So think of x. If you give me an x, then I'm gonna put that through the machine called T2 first, and that T2 will give you a result of T2 of x, and then you put that into the next into the other machine, which is T1, and the result is T1 of this input, is the output of this input, which is T2. So this is how you compute this composition. But on the grand scale, this is what we see. We see a pretty big box where you can put an x in and get a single result out. We don't care, or maybe we don't know about whatever is going on inside this machine. This big machine is T1 or T2, which is kind of not intuitive, right? Because T1 is on the left and T2 is on the right. But in computation, you have to do it from inside out, which is T2 first and then T1. So yeah, sometimes inside out, left to right, or things could happen. That's a transformation. And once you compute that, then you're gonna get a new transformation that may or may not be the basic ones. They may change. You might get a new term. You may get a new translation. You may get a new relation, or just maybe something else. For instance, maybe I should not do this first. I should start from 2. But the exercise is for 2 functions. So let's see. Yeah, there are 3 transformations. So you can, or you want to compose them. And there are 2 ways to compose them. First, you can do commutation, which is what we see in this first equation. Plug in the value of x and compute everything else. And you can also do it visually, which I don't have example in this in the slide, but I can write for you. I can draw it for you real quick. Okay, so let's start from visual. So what is going on here? So visually, let's see. Maybe we have 0. Let's say we start from 0 and 1. I should start from that. Let's say 0 is on the left, 1 is on the right. And so we transform it using this transformation. And remember that when we have a change, we start from inside and then go out. So the first thing we do is given a line segment or a number, and then we can use the last or the innermost composition first, or transformation first. So here we have 3 of x is minus 2 times x. Right, what does this mean? It means we we multiply that by minus 2. And the result should look like this. So we start from this line. We scale it up by 2 times, and then we flip it. We reverse it. The result is this line. Right, and then you can guess how we could continue. X plus 3. So from this one, if you move it 3 steps to the right, because it is plus, right, then the result should be 1, 2, 3. You move. Sorry. I should also maybe write that a little bit. 0 goes to 0, 1 goes to minus 2. Here, minus 2 goes to what? Go to 1, because minus 2 plus 3. If you translate by 3 steps, you get to 1. And also 0 becomes 3. That's a translation. That's the second step. And lastly, we multiply that results by 3. How does it look like? It looks like we need more space. So Yeah, there won't be enough. Okay, so I'm gonna do this. Not a good way to do that. Yeah, so I forgot to make a line segment. So we have this line from 1 to t. And once we multiply everything by 3, this point 1 goes to the point 3, and this point 3 goes to the point 9. So this line is stretched by 3 times. It has length 2, like at first, but now it has length 6. So that's the first part. Once you complete composting, that's the final result. Oh, and also finally, like this doing step by step. But of course, when we have this whole image, then you can think of this whole process like inside the black box as something you don't see. So all you see here, is that if you start from 0 and 1, first part, that's the second part. If you start from 0 and 1, then you're gonna get to 3, 2, 9. In the reverse order, and then this is important because we have a dilation by a negative number, and so the point 1 goes to 3, and the point 0 goes to 9. And so that's the composition of these 3 transformations condensed into one. And so that's the first one. If you do it visually, and that's the result. But of course, sometimes you don't see. You want to know more about this one because there are only like 2 points. So you're not sure what the result should be. So maybe you want some math. Yeah, let's do some math. So the way you do math, you do nested function is as follows. Okay, so we start from the innermost one, which is 3 of x. Oh, the logo is in the way. So 3 of x is minus 2x. Yeah, that's just, just copy this whole thing. And then use some blue then. The next step is to compute T2 of 3 of 3x. Because it is what we see on inside the parenthesis of T1. The way you compute this is you look at the definition. Like it says whatever value x you give me, I'm gonna put x here and add it by 3. So in this case, it gives you something. Suppose you don't know that, but nevertheless you can still find that. Like, T2 says you write that number, whatever you got given to, and add it to 3. So we write that number down, 3 of x, and then add it to 3. So this is the second step. Right, but again, you can see 3 of x plus 3. That can be simplified, right? 3 of x is what we just saw above here, which is minus 2x. And then plus 3. Okay, so that's the of the nested. And finally, we are ready to do the T1. Let me shade a little bit because I want to change the colors too often. So if you want to do T1 of the whole thing. So again, T1 is 3 times the number in parentheses. So it's 3 times whatever we have in the parentheses, which again, I'm gonna sheet by copy and paste that. So that's the whole thing. Like T1 of something inside is 3 times that inside. And what is that inside? It's something we just found earlier, which is 2x minus 2x plus 3. And so here it is. Like that's the transformation. And if you do some math, then you can distribute 3 inside the parentheses and get minus 6x plus 9. So that's the answer for this example. Visually, like it moved 0 to 9, moved 1 to 3. So it scales up by factor of 3, flip, and then move around. But the more precise definition is this function, which you can see that, okay, it flips something. That's the negative side. Like it scales a line by a factor of 6, and it moves things to the right by 9 units. So that's the example of how you compute and write and draw the one-dimensional transformation. It's a composition of smaller transformations. So that's the end of the part 1. That's exercise for you. See you in part 2.